Good morning, or afternoon, or whatever time you are watching this. Welcome to Unit 11. We are starting a new unit. The unit is redox, and what we'll learn today is actually a mix-up of two words, reduction and oxidation. So, to best go through this, it makes the most sense to watch this video as you are going through the notes. So, according to the schedule, it doesn't look like we have anything due tonight. Just make sure that you are following the schedule on the website or wherever your teacher posted. Okay, so getting started. Figuring out what redox is. So all of this depends on what's happening to electrons, essentially. So in this picture, we have CuO ends here. So here, this copper loses an oxygen, and we say that's reduction. And then this carbon gains an O, and we call that oxidation. So that's kind of where the term comes into play, but the definition we're going to be working with focuses more on electrons in general, not just oxygen. So, like I had said before, redox is a mix of reduction and oxidation, and we're talking about these types of reactions. So a redox reaction is something that transfers electrons, and so we will abbreviate that as E- throughout the unit. So that's what that means. And when this happens, reduction and oxidation need to happen simultaneously, meaning at the same time. So we're going to talk about what oxidation and reduction actually means, but just know that they happen at the same time. So reduction is the gain of electrons. And remember, electrons are negative, okay? If you're getting more electrons, you're getting more negative. And so the oxidation number goes down or reduces. So if you think back to your periodic table, let's just say carbon, for example, these numbers in this top right-hand side, those are possible oxidation states. So this is what we're talking about. This is what we're focusing on this unit. So for right now, reduction is the gain of electrons, and the oxidation number will go down. Oxidation, and that's where, going back a second, that's where reduction comes from. The number is being reduced. Oxidation, on the other hand, is the loss of electrons. And if you're losing electrons, you're becoming more positive because you're getting rid of all that negative stuff, and your oxidation number goes up. So a quick way to kind of remember this one's my favorite. Leo the lion says GR, and what this stands for is that loss electrons is oxidation, gain electrons is reduction. So that tells you what happens to the electrons and what part of redox it is. The other one that people like to use a lot is oil rig, which stands for oxidation is loss, reduction is gain. You just need to remember we're talking about electrons. So that's why I like Leo the lion better, but whatever, helps you the best is up to you. So when we're talking about these redox reactions, or any reactions in general, we've talked about how energy needs to stay conserved. So you can't just magically lose or create energy out of nowhere. Mass has to stay conserved. That's why we balance equations. You can't just magically lose or gain stuff during a reaction. And conservation of charge also needs to stay the same. So what that means is that the charge in the beginning of the reaction has to be the same as the charge at the end. So if one atom is losing electrons, those electrons don't just magically disappear. They're gained by something else. So that's kind of what redox is. Something is losing electrons, and as something is losing it, something else is picking up those electrons. So that's what we mean by these two reactions, reduction and oxidation, happen at the same time or simultaneously. So here's where the vocab words get a little kind of confusing. So the substance that loses electrons, so it's being oxidized, we call that the reducing agent. So that's what allows something else to be reduced. The substance that gains electrons, so remember gaining electrons is being reduced, is the oxidizing agent. which means it can allow something else to be oxidized. So if we look at this example, we have magnesium with 2 valence electrons, we have sulfur with 6, and we get a magnesium 2+ ion. Remember, this means it lost 2 electrons. This -2 means it gained 2 electrons. This kind of helps see it. So let's walk through this example in more detail. So, with this, magnesium starts off having 2 valence electrons, and then we see at the end, it doesn't have them, it lost it. So we can say it lost electrons, and because of Leo the lion says Gur, losing electrons that means it's being oxidized. So if magnesium is being oxidized, that means it acts as the reducing agent. Now, if we look at sulfur, it has 6 valence electrons. At the end, now it has 8. So in order to get from 6 to 8, you have to gain electrons. So again, gaining electrons is being reduced, and whatever is being reduced acts as the oxidizing agent. Okay, so when we're working with these redox reactions, a lot of it's focused on what happens to these oxidation numbers. And so we're gonna practice with this essentially all unit. So this unit kind of builds and this unit definitely builds on what we did the day before, and everything kind of gets wrapped up together. So if we're looking for redox reactions, and this is kind of the focus of tomorrow, you want to see if the oxidation number from an element at the beginning of the reaction, so as a reactant, changes its oxidation number when it's a product. If that oxidation number changes, that means it either lost or gained electrons, which means it is a redox reaction. Again, these oxidation numbers are used to kind of track the movement of these electrons, so whether it's losing electrons or gaining them. So these oxidation numbers, these oxidation states, mean the same thing. They can be positive, negative, or even 0. So the periodic table, each element has these oxidation states, and there are more that exist, but this is just kind of a good place to start. And so depending on what it's combined with, it tells you how many electrons it lost and or gained. Now, generally speaking, the top number is the most common, that's why it's on top, but that is not to say it can't be any of the options. So when we try assigning oxidation numbers to elements, we're not always going to use that first one, and that's totally okay. It just takes kind of practice, and we're going to work on that shortly. So a few quick tricks to determine if something is a redox reaction, and again, this will make more sense later and tomorrow, is that a single replacement reaction is always redox. So tomorrow you'll see, maybe even later, you'll see why. But single replacement is always redox because the oxidation numbers do change, and you'll see why soon. Now, a double replacement is not a redox reaction. So if we were to find the oxidation numbers for each of these elements in each compound, you'll see that they do not change. So again, kind of this point needs to be driven home a lot. Oxidation numbers, if they change for 2 elements, that is a redox reaction. So again, reduction meaning something is gaining electrons, so over time the oxidation number goes down, because if you're gaining electrons are negative. If you get more negative stuff, you become more negative, so you decrease. And if you're oxidized, you're losing electrons, and if you're losing that negative stuff, your oxidation number goes up. So there are some rules to assigning oxidation numbers. I'm going to go through these pretty quickly because it just makes more sense to jump into practice with them. So this is one of the most important ones. Elements by itself or uncombined always has an oxidation number of 0. So that means anything by itself, this one copper atom, or this diatomic molecule of H2. If there's only one element, the oxidation number is 0. If you have an ion, so whatever that charge is, that's the oxidation state. So if you see S with a 2-, the oxidation number is 2-. If you see aluminum with a 3+, that means the oxidation number is 3+. Anything in group 1 has an oxidation state of +1. Again, these rules aren't something you really need to memorize that much because it is on the periodic table. Anything in group 2 has a +2 charge, again, straight from the periodic table. Hydrogen, so this is a kind of important one. And when you're assigning these, you'll kind of see this as you're moving through these questions. So H has two options, +1 and -1. When H is with a non-metal, it generally is +1. And when it is with a metal, it is generally -1. So that does help in some of the questions, but you also need to kind of just play with it. Number 6, oxygen 99% of the time is -2, except for when it's in a peroxide formula. And I doubt at this level you'll see them, but it would be something to O2, and then it would be a -1 oxidation state, but those are so rare, and again at this level I doubt you'll even see that. Number 7, fluorine is always -1. If you look at group 17, so that column number 17 on the periodic table, a lot of these halogens do have multiple oxidation states, but fluorine is only -1. Number 8, if you have a polyatomic ion, so let's say OH- or something else, the sum of these oxidation states would be the charge of that polyatomic ion. For a normal compound, a neutral compound, when you add up all the oxidation states, it should add up to 0. If it's a compound and your oxidation states do not match up to 0, that means you did something wrong. So this is another super important one. And so we're going to go through and practice these to make this make more sense. So, I'll do half and then you do half. So all these elements are by themselves. So anytime you have an element by itself, its oxidation number is 0. For number 2, it's by itself, it's 0. For number 3, even though it's H2, it's still one element, so it's 0. So all of these have an oxidation state of 0. So with these, now we have ions. And you have to look at these numbers up here. They tell you what the oxidation state of that ion is. So for zinc 2+, the oxidation state is +2. For chlorine -1, it's -1. And so these ions are very, very, very easy to identify. And that's it. When we jump into compounds, though, this is where it gets a little bit tricky. Now, I love to use this table format because it definitely organizes everything you need to know. So, you have your compound. You break it up by elements. You have C and you have O. And then subscript, sub stands for subscript. So we have 1 carbon and this should be 2 oxygens. Okay? So, oxygen we know always has an oxidation state of -2. And so if one oxygen has a -2 state, if you have 2 of them, 2 times 2 gives you -4. Now we know the total has to equal 0. So whatever the carbon is plus whatever the oxygen is has to be 0. So at this point we know oxygen is -4. So that means carbon has to be +4. Now, if carbon is bringing a +4 charge and you only have 1 carbon, that means the oxidation state of carbon is +4. So let's go through a few more. for calcium hydroxide, the table's already set up for you, so that speeds this process up a little bit. We have 1 calcium, we have 2 O's, and we have 2 H's. Remember, this little 2 only talks about whatever is in that parentheses, so it's the same thing as saying COH, OH. So that way it's easier to see you have 2 O's and 2 H's. Now, calcium is always plus 2. And so if you have 1 calcium with a plus 2 charge, 1 times positive 2 is positive 2. Oxygen, we know, is negative 2. And if we have 2 of them, we have 2 times negative 2 is negative 4. And we know that positive 2 plus negative 4 plus something gives you 0. The only thing that can make this equation possible is a positive 2. So that means hydrogen needs to bring a total of a positive 2 charge. Now, we have two hydrogens to bring that positive 2 charge. That means each hydrogen has to have a plus 1 charge. And that is everything you need. Moving forward to the next one, we have water. So in this we have 2 H's, we have 1 O. Oxygen is always negative 2. It's a good place to start. If you have 1 negative 2 thing, that means your total negative is negative 2. We know something plus negative 2 gives you 0. So the only thing that fits in is a positive 2. So that means both of those hydrogens in total bring a positive 2 charge. So that means 1 H only has a positive 1 charge. So if you have 2 H's in total, and the total positive is plus 2, it means each individual H brings a positive 1 charge. And that's it. Number 4, magnesium phosphate. This one gets a little bit trickier, but we can do this. With this, we have 3 magnesiums, we have 2 phosphoruses, and 8 oxygens. So I like starting with oxygens. Again, we know that's negative 2. And if you have 8 things each with a negative 2 charge, that is a total of negative 16. We know that total is going to be 0. So something plus something, something plus negative 16 gives you 0. So magnesium is in group 2 and has a positive 2 charge. And so if you have 3 things, each of which have a positive 2 charge, that means you have a positive 6 charge for all of magnesium. Now, one of the reasons we saved phosphorus for last was because it has a bunch of different options. But now we can kind of narrow that down to pick the exact one. So if we know that 6 plus something plus negative 16 gives you 0, the only thing that makes sense in this box is 10. So that means in total, the 2 phosphorus things need to bring a total of a positive 10 charge. So if you have 2 things with a total of positive 10, 10 divided by 2 gives you positive 5. So each phosphorus has a plus 5 charge. And that's it. So these all work the same way. So let's continue with ammonium chloride, We have 1 N, 4 H's, 1 Cl. Cl is always negative 1, so that's easy, you can just bring that down. We know something plus something plus something equals 0. Now, nitrogen has a few different options, so let's save that one for last. Hydrogen, we had said, when it's with nonmetals, has a positive 1 charge. So if you have 4 H's, each of which have a positive 1 charge, you have a total of positive 4. And so now we can figure out what N has to be. So something plus positive 4 plus negative 1 gives you 0. And the only thing that makes sense in this equation is a negative 3. So if you have one N that brings a negative 3 charge, it means the oxidation number is negative 3. And lastly, number 6. Let's make this a tad bit more complicated. Now we're going to deal with a polyatomic ion. And so one of the rules we had said before, the sum of the polyatomic ion needs to be whatever the charge of the polyatomic ion that it is. So here we have a negative 2 charge. That means something plus something has to give us negative 2. Now again, the reason this is not 0 is because we're dealing with a polyatomic ion. Any neutral compound is always 0. So if we look at this, we have 1 carbon, we have 3 oxygens. Oxygen has a negative 2 charge. If you have 3 oxygens, each of which have a negative 2 charge, that is negative 6. And so if we're working on this, that means something plus negative 6 gives you negative 2. And the only thing that does that is positive 4. And so that means carbon has a positive 4 charge because there's only 1 carbon to bring that total charge. And that's it. So we're going to be working with this chart a lot more tomorrow and throughout the unit. But there are a few more questions I want to go through with you now. So these are some Regents-style questions. Take a second to kind of look through it, and then we'll go over them together. So for number 1, it says, what are the 2 oxidation states of nitrogen? So I'm just going to do this shorthand a little bit to speed this up. We want to look at what the 2 N's are. So we know oxygen is always negative 2. And if you have 2 oxygens, that means you have a total of negative 4. If we have hydrogen, we're dealing with only nonmetals. That means this is a plus 1. And if we have Ox number, I'll put total on the bottom so you know what I'm doing. If you have 4 positive 1s, that is a positive 4 charge. So as of right now, not looking at the N's, we have plus 4 and minus 4, which is 0. So we know that something plus positive 4 plus something has to equal 0. So the only option that makes that equation fit is plus 3 and minus 3. It doesn't matter which N is positive, which one is negative, just that the entire compound still has a charge of 0. So number 2 asks for the oxidation state of manganese, which is Mn. So we can do the chart. We have KMnO4, KMnO, and leave some blank. Subscript, oxidation, total. Once you get more comfortable with this, you can kind of skip the chart like I did for the first question, but it's up to you. So again, we know this is going to equal 0. We have 1K, 1 Mn, and 4 O's. Mn has a bunch of options, so let's save that for last. O is negative 2. If we have 4 of those, that's a total of negative 8. K is plus 1. So that means if you have 1 of those, that's a total of plus 1. So the only thing that makes this equation 1 plus something plus negative 8 equals 0 is positive 7. And if you have 1 Mn to bring this total positive 7 charge, that means its oxidation number is positive 7. Number 3, this is talking about just the oxidation number of N in NH4Br. So let me show you the short way about doing this. We do the oxidation number and the total. It's the chart, but a little bit less organized. So Br is negative 1. So you have 1 of them, that's a total of negative 1 charge. We're still dealing with just nonmetals. So H is going to be positive 1. If H is positive 1 and you have 4 of them, that's a total of plus 4. So something plus positive 4 plus negative 1 has to equal 0. The only thing that fits in that equation is negative 3. Moving forward with this one. Again, I'm going to go through the short way. We have Na2, S2, O3, ox, total. So oxygen is negative 2. If you have 3 of them, that's a total of negative 6. Na is always plus 1. If you have 2 of them, that's a total of positive 2. So positive 2 plus something plus negative 6 has to give you 0. And the only thing that fits in to this is positive 4. Now, positive 4 is not the answer, because this is saying that in total, both sulfurs are bringing a total of positive 4. But notice there are 2 S's. So that means both those S's together bring a total of positive 4. So if you have 2 things in a total of positive 4, one thing brings a charge of positive 2. Okay. That's kind of a tricky one, but that's as tricky as these kinds of questions get. Number 5 talks about how does the oxidation state of chlorine change. So if we write this over here, ClO3, 2 KCl plus 3 O2. I'm just going to walk through it the short way. So let's look at this compound first because it's smaller. Cl is minus 1. K is plus 1. So K is always plus 1, which means we know chlorine has to be minus 1. So you get a total plus 1 here, minus 1, you get 0, which is good. Okay, so we know that chlorine is going to end with a minus 1 charge. So right off the bat, we can get rid of A and B. So looking at this one, again, we know K is always positive 1 because it's in group 1. So if you have 1K, it's a total of positive 1 plus something. Now, oxygen has a negative 2 charge. If you have 3 of them, that's a total of negative 6. And so the only thing that fits into the box to make the equation equal to 0 is positive 5. And notice there is only 1 chlorine. So it means that 1 chlorine brings that positive 5 charge. So chlorine is going from positive 5 to negative 1. So this is an example of a redox reaction because you can see that these oxidation states are changing. Number 6, the last one for today, is the oxidation number of chromium in the chromate ion. So let's use the box for this. So we have Cr, we have O, leave ourselves some blank room, subscript, oxidation number, total, and we don't really care about that section. So here, the most important thing is that the total is going to equal negative 2 because we're dealing with this polyatomic ion. So we have 1 chromium and 4 oxygens. So if you look at the periodic table, chromium has a bunch of different possibilities. So let's wait for last. Let's save that one for last. Oxygen we know is negative 2. If you have 4 things, each of which have a negative 2 charge, that is a total of negative 8. So that means something plus negative 8 has to equal negative 2. And the only option that fits is positive 6. Now, there's only 1 Cr in this compound. So that means that 1 chromium needs to bring the total positive 6 charge, which makes the answer for this question A. So that is it for oxidation numbers right now. We will practice with this tomorrow. But that is it. On that note, have a wonderful day.